There are two possible ways in order to multiply them. One is dot product and the other one is cross product. So we do know that motion exists in a straight line, that is known as linear motion or simply rectilinear motion. And now we also have to find a relation between angular velocity and linear velocity. Dividing throughout by t, we will get the equation for centripetal acceleration. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with motion in a plane. And this is the last session of this particular chapter. So, what are we going to learn today? So, we learned about vector addition in the previous classes. Now, we are going to learn about vector multiplication. So, what exactly is this vector multiplication? So, we do know that there are certain quantities that is vector quantities that cannot be directly added together or multiplied together because they have different directions and different magnitudes. So, if they only had magnitude quantities or if they were just scalar quantities, we can add them or multiply them just like normal numbers. But right now, it is not as such because they are vector quantities. Since they are directionally different, we cannot use conventional methods of algebraic operations on them. That is, simple addition and simple multiplication just won't work on them. So that's why we have something known as vector multiplication. So you will actually learn this in the PU second year in mathematics chapter, but for now we need some basic concepts so that we can continue on with our physics. So if we have two vectors, that is vector A and vector B, we have two different ways in order to multiply them. So the first method is known as dot product and the second method is known as cross product. Dot product and the second method is known as cross product. So how this dot product actually functions, how this cross product actually functions, everything will be discussed in the coming chapters actually, because we need these sort of multiplications and these operations in the coming chapters a lot. So I'll be explaining what this dot product means, what this cross product means, why is it necessary. By the way, it is necessary because there is a directional aspect to this vector quantities, but everything will be explained in the coming chapters. So for now, we will just learn the definition or how we can do these operations for now. And in the later classes, I'll discuss in detail why and how this particular dot and cross products behave the way they behave. So if there are two vectors, vector A and vector B, then we can say that there are two possible ways in order to multiply them. One is dot product and the other one is cross product. So first, we'll discuss about what is dot product. So let's say we have two vectors, vector A and vector B, and they are acting at an angle theta. So then we can say that vector A dot vector B will be equal to magnitude value of vector A into magnitude value of vector B into the cos of the angle in between them. That is, the cos of the angle between them will give you the definition of dot product. So this is the actual definition of dot product. That is, if you have two vectors and if you take the dot product of them, then it will be equal to magnitude of vector A into magnitude of vector B into cos of the angle in between them. Now, since we are taking the magnitude values and just the angle between them, this quantity is now converted into a scalar quantity. There is no directional sense to this particular part. So, we can use this to convert any vector quantity into a scalar quantity also. But for now, we only need to know that this particular operation is defined as such. And just like this, we can define cross products also. That is another vector, that is vector A and vector B, and angle between them is theta. Then vector A cross vector B. So this is not the into sign, this is known as cross. And this A into B is actually read as vector A cross vector B. So in terms of vector, when we multiply them using this symbol, it is known as vector A cross vector B. Now, vector A cross vector B will be equal to magnitude of vector A into magnitude of vector B into sine of the angle in between them. So this is the definition of dot product and this is the definition of cross product. So it is very simple. You only have to know that A dot B will always be equal to AB cos theta and A cross B will always be equal to AB sine theta. Now, why this sine theta is coming, why this cos theta is coming, will be explained very soon. But for now, just know that this is how we can do vector multiplication in the dot product form and in the cross product form. Why these angles are there will be shown to you very shortly. But for now, just understand the definition or the expansion of this particular forms. There are two types of operations. That is, one is dot product and one is cross product. One is AB cos theta, the other one is AB sin theta. And the very next important thing you have to remember is that when we are applying dot or cross products to vector A and vector B, we are not just multiplying any two scalar quantities. There is also a directional aspect in between them that is indicated to the unit vectors, or just like, for example, we can say that if there is any quantity like this, then it is not just the magnitude value of these particular quantities. There is also a directional aspect. Three directions are also indicated. So if there are two vector quantities, let's say 1i plus 3j plus 3k. If there are two vectors and we are taking the dot or cross product in between them, we are not just multiplying scalars together. We are also multiplying or taking the dot or cross products of I dot I, j dot j, k dot k, or I cross I dot j cross j, and k cross k. Like that, we are taking the cross products of the directional aspects also. That is, the vector components are also undergoing this algebraic transformations. So we have to know how we can multiply or we can perform these operations on the base vectors or just the unit vectors. So if you're just taking the dot product of this particular quantity, that is, if you're taking the dot product of the base vectors, then what will be the answer? That is, we do know that the base vectors are actually three mutually perpendicular axes in space, or simply the angle between them is 90 degrees. That is mutually perpendicular to each other, and I is nothing but x-axis and j is nothing but y-axis and k is nothing but the z-axis. All the unit vectors of these particular axes are denoted as I, j and k unit vectors. Now, if we take the dot product of this particular quantities, it just means that magnitude of I into magnitude of I times cos theta, the angle between I and I. That is, if I am taking the unit vectors both in the same axes, then I can see that these are not two perpendicular lines. These are actually two parallel points, which means that if it is two parallel points, the angle between them will always be 0. So it is cos 0. And we do know that cos theta when equal to cos 0 is actually equal to 1. Because sin 0 is 0, which means cos 0 is actually 1. So cos theta becomes cos 0, which is equal to 1. So I dot I will be equal to 1. Now again, the magnitude value of I into magnitude value of I into cos theta. Magnitude value of a unit vector. Unity means 1. So unity means 1 itself. So I into I, which means magnitude of I into magnitude of I. It is not I square. It is 1 into 1. You can take it as 1 square, but again, It is 1 into cos 0. Cos 0 is again 1. So it is 1 into 1 into 1, which is nothing but 1. Just like that, every unit vector quantity is denoted here. That is I dot I or j dot j or k dot k, everything will be equal to 1. So we can say that this will be equal to 1 and this will be equal to 1. Or simply we can write generally that I dot I will be equal to j dot j will be equal to k dot k will be equal to 1, because the angle between these are 0. I and I are on the same plane, which means they are parallel to each other because the angle between them is 0 degrees. Same is for j dot j and k dot k, which means the answer will be equal to 1. If we take the dot product, that is a dot b is equal to ab cos theta, or I dot I is equal to I cos theta, which is equal to 1. So it is true for I dot I, j dot j and k dot k. Now, what if we take in between them? That is I dot j and j dot k and so on. That is, I am taking the dot product of I and j vectors. Now what will happen? Now the angle has actually changed. Now the angle between I and j is actually 90 degrees because they are mutually perpendicular to each other. So then we can actually write that I dot j will be equal to magnitude of I into magnitude of j into cos of the angle between them. So here the angle between them is 90 degrees. So we can say that theta is equal to 90 degrees, which means cos theta will be equal to 0. Cos theta will be equal to 0 because the angle between x and y axis is actually 90 degrees, or simply we can say that they are mutually perpendicular axes, which means cos of the angle between them is 90 degrees and cos theta is actually equal to 0 because cos 0 is 1, cos 90 is 0. I dot j is actually equal to 0 and j dot k is also equal to 0, k dot I is also equal to 0 because the angle between these axes are 90 degrees. They are mutually perpendicular. Since the angle between them is 90 degrees, if we take the dot product between other unit vectors or other vectors, it will be equal to 0. So, if I am taking I dot k or I dot j, it will be equal to 0. If I am taking k dot I, it will be equal to 0. If I am taking j dot k, it will be equal to 0 because the angle between them is 90 degrees. If I am taking I dot I or j dot j, it will be equal to 1, unity, because the angle between them is 0 degrees. Here it is 90 degrees. So we also have to learn about cross products, but in actuality you only need a dot products at this particular juncture, but in the future stages you will also need cross products. But for now, just know that if we take the cross product of these are the values we will get. That is, I cross I will be equal to magnitude of I into magnitude of I into sine of the angle between them. So sine theta, here theta is equal to 0 degrees because again they are parallel points. If this is the I-axis, I am taking 2 points here and here, or 2 points here and here, which means they are parallel points, which means the angle between them is 0 degrees. So I into I of sine of the angle between them, sine theta is here, sine 0 is nothing but 0. So theta is equal to 0 degrees, sine 0 is equal to 0. So we can say that this will be equal to 0, this will be equal to 0, this will be equal to 0. And that is all about I cross I, j cross j and k cross k. But you also have to know about what is I cross j. That is, we are measuring the angle from this way, right? That is, we are measuring towards the left. From the horizontal, we are measuring the angle towards the left. So that is how we will actually go with this particular measurements also. That is, when we are taking the measurements of these particular quantities, that is I cross j, mutually perpendicular axes, I, j and k, we will go towards the left because if we go towards the right, the angle will actually change. Remember, these are vector quantities, so direction is very important. So if we go in the opposite direction, what will happen is that the angle will change and we have to introduce a negative sign. So that is why for easiness, we'll say that we'll go generally from the horizontal to the left hand side. So when we are measuring from the horizontal to the left hand side, what we get out of these is actually when we measure I cross J, we will get, when we measure I cross J, we will actually get the next axis. That is, when we are measuring I cross J, it will actually give us the next axis, which is K. I cross J will actually be equal to unit vector K. Why that happens will be explained. Don't worry about it. You don't actually need the explanation, but for your sakes, for you to understand this much better, I will explain what is cross product, what is dot products, why these axes are behaving in this particular manner. I will discuss that, but that itself requires an entire class. So I'll discuss that later. So just remember for now that I cross J will give you the next mutually perpendicular axis. In this case, it is K. And same way, if J cross K is taken, it will give you the next mutually perpendicular axis. Here it is I. So J cross K will give you I, and K cross I, that is K cross I will give you the next mutually perpendicular axis. In this case, it is J. So it will give you unit vector J. So remember, if we cross the very close by unit vector axes, when we are taking the angle towards the left, it will give you the very next axis. What happens if you are taking the angle in the right hand side? That is, what happens if I take, instead of I cross J, I take J cross I. So what will happen then is that if I take J cross I, what will happen is that the angle now is changing. So we know that angles are measured from the horizontal to the left. So when we are measuring in the opposite direction, the direction is different, which means we have to introduce a negative sign. So we will say that this will be actually equal to J cross I. J cross I will always be equal to K, but in this particular case, since we are taking the reverse direction, it will be equal to minus K. And similarly, if I am taking I cross K, then this will be equal to, that is, if I am taking I cross K, then this will be equal to minus J. And similarly, K cross J will be equal to minus I. That is, K cross J will be equal to minus I. So the only difference here is that, so when we flip this over, that is, when we flip these unit vectors while taking the cross product, the angle between them changes, or the direction which we measure the angle change, and then we'll get the quantities in the opposite direction, or simply we can say that the negative part of those quantities will be displayed. How this happens is a long sentence, so I'll show it to you very shortly. Don't worry about it. But just for now, remember that this is how we will get if we take the cross products and dot products of these particular quantities. So now we are going to learn about a new topic, that is centripetal acceleration. Before learning what is this particular centripetal acceleration, I'm going to direct your focus onto something new, or something you may not have been focusing on too much, that is circular motion. So we do know that motion exists in a straight line, that is known as linear motion, or simply rectilinear motion. There is also curvilinear motion. Motions are of many kinds, but we mainly focused on motion in a straight line, or one-dimensional motion, or linear motion in the previous chapter. Now we are in a plane, that is, in this particular line, I only could move in one direction like this. But now my directional capabilities have been increased. That is, I can now travel anywhere within this plane, which means that I can actually execute an angular maneuver, or simply I can go around in circles. So when I am executing a particular motion in a circular pattern, or in an angular pattern, or in a curvy pattern, I can say that I am actually executing a circular motion. So we have to learn about circular motion and the quantities relating to that particular circular motion. Our world is not built in a linear line. Sometimes we have to take turns. Sometimes we have to go in circles. Sometimes we have to go in spiral ways, like a roller coaster. So we have to know what is the physics behind all that, because our job is to find out how things happen and why things happen the way they happen. So if any object is executing a circular maneuver like this, we have to know what is the physics behind it. We have to know what is the displacement, what is the velocity, what is the acceleration, what is the force behind it, everything we have to know. So, in order to find that out, we are going to try, can we use linear mechanics on this? No, because linear mechanics are for linear quantities. This now is executing a circular motion, which means we have to apply rotational motion or rotational mechanics on this particular type of motion. So consider this, there is a particle, let's say this is a car, and this car is going around a round track really fast. So it is executing a uniform circular motion, or simply we have to define what is uniform circular motion. We know that circular motion means that when an object is traveling in a circular path where the radius is fixed. So that is circular motion. What is uniform circular motion? Uniform circular motion means that if that particular object is traveling around in a circular motion with constant speed, then it is known as uniform circular motion. That is, if this car is going around the circular track in 50 km/h speed throughout its journey, then we can see that it is a uniform circular motion. Now, speed is throughout same. That is, the speed throughout this particular track for this particular car is same, 50 km/h. But is the velocity same? The velocity is not actually same, because at this particular point, the velocity is in this particular direction. But if I take this particular point, the velocity is in this particular direction. Even though the speed is same, it is 50 km here, 50 km here. But actually, the velocity is different. Why is it different? The magnitude value is same, 50. The magnitude value is same, 50. But the direction of velocity vector changes. First, it was in this particular direction, let's say in the y-axis. Now it is in the negative x-axis, which means the direction is constantly changing. Since the direction is changing, we can see that velocity is actually changing. In this particular case, only velocity is changing, but constant speed is remaining. Velocity is changing only because direction is changing. Constant speed is maintained. Hence, this is a uniform circular motion, but velocity is continuously changing because direction is continuously changing. You can relate this to the earth spinning around the sun, or a stone going around in a circular path where it is tied to a string. Everything can be imagined in this particular circular motion. Velocity is constantly changing. The direction of velocity is changing, but the speed is remaining constant. The speed can also change. Then it will be just circular motion, non-uniform circular motion. In this particular case, I'm assuming that speed is remaining constant, which means that it will be a uniform circular motion. So let's imagine that this particular circle has a radius of r, and this particular object, let's say this particular car, is executing a circular motion here. So in terms of linear velocity, that is, if the car was traveling in a straight line, I can say that the way we can find the linear velocity is actually equal to v is equal to displacement, I'm taking it as s by t. That is, linear velocity will be equal to displacement divided by time. What about here? It is not going linearly. That is, it is not going in a straight line, but rather in a circular path or at an angle. So we can call this as angular motion, or simply we can say, instead of linear velocity here, we are going to write it as angular velocity. That is, if this particular object is executing a circular motion, then the velocity it experiences is known as angular velocity. It is traveling at an angle, or simply it is executing a circular maneuver. So it will be at an angle. That is why it is known as angular velocity. And this particular velocity is known as linear velocity. So this is known as linear velocity. Now we are going to learn about angular velocity. Angular velocity, omega. This is indicated by the small letter omega, and omega will be equal to, just like analogous to linear velocity, angular velocity will be equal to, how can we find that out? It's very simple. So we'll assume that it traveled a small distance, that is, it traveled a small distance like this. So that particular small distance is taken because when we are taking a large distance, the curve will be too much. If I'm taking a very small distance, the curve will almost seem like a line. So I can take that particular length. That is why I'm taking it. But since you can't see that very small line, what I'll do is that I'll take a large line like this. Okay, I'm taking a large line like that, and I'll say that, okay, distance covered linearly will be like this. So there is a gap here, right? There is a gap here in between that particular line I have drawn. That is the edge of my triangle, and the curve has a gap. In order to avoid that gap is why I took a very small line. But you can't see that, so I'm taking a bigger line. Just know that it will be a very small line, and the gap between these two will be very small if I'm taking a smaller angle. But you can't see that. For that purpose, I am drawing it very large. So again, then we can say that this is position 1 and this is position 2. If this was linear velocity, again, the way we would find velocity will be change in displacement divided by time taken. We will apply the same formula here because we are going to find something known as arc length. So at very small angles, this particular quantity, that is this particular distance, will be blended with the circle, which means that if I find this particular length, it will be equal to my displacement. So if I want to find this particular distance, I need to know what is this particular arc length. That is, this particular section of the circle is known as arc length. So we do know what is the formula in order to find out what is arc length. We learned it in the first chapter. So in order to find out the arc length, I'm going to use a simple principle we learned in the first chapter. So we can simply say that this distance covered, that is arc length, is this particular distance. In this particular case, we can say that that particular distance covered will be equal to the displacement of the particular car. So we can say this will be equal to S. So that is the arc length is equal to S. And we already know theta. So theta is equal to arc length by radius, or simply we can say that theta is equal to arc length divided by radius. Here theta is the angle, arc length is the displacement of that particular quantity or particular car, and r is the radius. So theta is equal to S by r. Now why did we find out theta? Because in angular velocity terms or in angular motion terms, we can say that theta determines the angular displacement. That is, in linear terms, I can say that it went from position 1 to position 2 like this. But if it is at an angle, that is, if it is executing a circular motion, I cannot say that, okay, it traveled from here to here to here linearly. I have to specify that particular change. So if it is a circle, what better way is there to specify than an angle? That is, it moved, let's say, 1 degree, or it moved 10 degrees, it moved 90 degrees, it moved 45 degrees, like that. So in a circular motion, theta determines the angular displacement. So theta is known as angular displacement. Just like we have linear displacement, we also have angular displacement. And the relation between angular displacement and linear displacement is such, that is, theta will be equal to arc length divided by radius, or simply we can say that the relation between angular displacement and linear displacement is such. Theta is equal to displacement by radius, or simply theta r is equal to S. Angular displacement and linear displacement are related as such. So we now know a relation between angular displacement and linear displacement, and we also know that linear velocity is displacement by time. Just like that, analogous to that, angular velocity will be equal to angular displacement by time. So angular displacement is theta and time is nothing but time. So we know that this is angular velocity and this is linear velocity. And now we also have to find a relation between angular velocity and linear velocity. So in order to do that, I am taking this particular relation, that is theta is equal to S by r. Now what I am going to do that, I am going to divide this equation throughout by t. I'm going to divide it throughout by t, which implies this will be equal to theta by t is equal to s by t into r. So we already know that theta by t is nothing but angular velocity. So theta by t is nothing but angular velocity, which is equal to s by t, that is displacement by time, which is nothing but linear velocity by radius. So angular velocity and linear velocity are related through this particular equation, that is omega times r is equal to v. So that is one more relation you have to remember, that is angular displacement will be equal to linear displacement by radius, and angular velocity will be equal to linear velocity divided by radius. Those are two relations you can quickly remember. Now we are going to learn about the important topic, that is centripetal acceleration. So we do know what is acceleration. Acceleration is change in velocity. So is the velocity here changing? Of course, I just told you that the direction is changing throughout this particular journey, which means velocity is changing, which means there is acceleration produced, and since it is executed in a circular maneuver and the force is directed inwards, it is known as centripetal acceleration. Centripetal forces are those forces which are directed inwards. Centrifugal forces are those forces who are directed outwards. Imagine the earth and the sun. That particular force is directed inwards. Earth is trying to fall into the sun every second. So that is, the forces are attractive or the forces are directed inwards. That is due to gravitational force. Here it is due to some other force which we will learn in the very next chapter. For now, just know that centripetal acceleration is directed inwards. For now, just know that there is acceleration here because the velocity component is constantly changing. The velocity component is changing because the direction is constantly changing. Initially, if I take one point at Q, velocity is in this particular direction. If I take another point, let's say R, velocity is another particular direction. Make no mistake, the magnitude value is same. That is, it is executing a constant maneuver with constant speed, or simply it is executing a uniform circular motion and the speed is same, which means magnitude value of that particular velocity is same but direction is different. So we can write it as vector v1 is actually equal to magnitude value of vector v2. Magnitude values of vector v1 and v2 are equal. Let's call it as v. I'm going to do something you have learned in your previous class, that is in class 10th. So we can say that there are two vectors here or simply two tangents. That is, this is a particular tangent at a particular point. This is another tangent at a particular point. I'm going to take these two tangents outside. I'm just going to bring this outside so that there is one tangent like this. There is one tangent like this. So these two vectors, vector v2 and v1 are taken out like this. Now we have to remember that if two tangents are taken out like this, if this is the angle between the 2 points, that is the angle is theta, then the angle between the tangents will also be theta. That is a result you have learned in your 10th standard. So this angle will also be theta. Now one thing you have to believe me is that this particular vector, that is, if I close this triangle like this, then this particular vector will be delta V. Now we have two triangles, that is triangle, let's name this as ABC. So we have two triangles, that is triangle ABC and triangle PQR. There are two triangles right now. Why I did this makes sense very soon. So what is special about these triangles? These triangles are very similar, that is, two sides are equal, that is vector v1 and vector v2 has the same magnitude value. If I take it as length, these two lengths are equal. So these two sides are equal and this angle is equal to this angle, and these two sides are also equal because this side is also radius, this side is also radius, which means that these two sides are also equal. So these two triangles are actually similar triangles. And you have also learned something in your 10th chapter, that is, if two sides and the angles are equal, then by angle similarity rule, I can write something. That is, by angle similarity rule, angle similarity rule, I can write that triangle ABC is similar to triangle PQR. Triangle ABC is similar to triangle PQR, which means that whichever operations I do here will be similarly reflected over there. That is it. So just now, we are going to consider something else also. So this is nothing but displacement. We have just seen that this is displacement. Now I'm going to find out what theta is. So we know that theta is equal to arc length divided by radius. We already know this particular relation, that is angular displacement is equal to linear displacement divided by radius. Now this particular angle theta is equal to arc length divided by radius. This particular angle theta is equal to this side, that is delta V divided by this particular side or this particular side. It does not matter because two sides are same. So we can see that this is also equal to, that is theta is also equal to delta V divided by V2 or V1. Since V2 is equal to V1 is equal to V, we can just simply write it as V. So theta is equal to S by R in one triangle, theta is equal to delta V by V in another triangle. Since these two triangles are similar, I can write S by R is equal to delta V divided by V. Now let this be equation 1. Now what I'm going to do is that I'm going to divide this equation throughout by T. So I'm going to divide equation number 1 throughout by time. So then we will get S by T into R is equal to delta V by T into V. So we know that S by T, that is displacement by time, is nothing but velocity. So velocity divided by radius is equal to delta V by T, that is change in velocity divided by time is nothing but acceleration. Acceleration divided by V. If we rearrange this equation, that is if I bring this V to the left hand side, I can write it as V square by R is equal to A. That is, for any body that is executing a circular motion, that particular acceleration, that is, if any body is executing a circular motion, it needs to change its direction frequently. If it is changing its direction frequently, there is a change in direction for the velocity vector. If there is change in velocity, there is acceleration being produced. And in order to find out that particular acceleration, we can use this particular relation, that is V square divided by R. And this particular acceleration is known as centripetal acceleration. So just for that, since it is centripetal acceleration, I'm going to put it in a box and say centripetal acceleration AC is equal to V square divided by R. This is the relation between, or this is the formula in order to find centripetal acceleration. Where this comes to use will be soon found out in the very next chapter. But for now, remember that this is centripetal acceleration and this is the equation in order to find out centripetal acceleration. So what we did was we considered an object, let's say a car, which is going around a circular path in uniform speed, or simply we can say that we considered an object which was executing a uniform circular motion. In this particular case, it was a car going around in a circle, let's say at 50 kilometers per hour speed. So, which means that it is executing a circular maneuver with constant speed, uniform circular motion. Now, at 2 points, we took the velocity vectors. One was vector v1 and one was vector v2. So these particular vectors had different directions but same magnitude quantity. So again, then we took these two vectors outside, made it into a triangle. So these two vectors, since they were acting at an angle, we made them into a triangle. And then when we observed this particular triangle, we knew that we could make this triangle because we learned a property in our 10th standard, that is, if two tangents can be drawn like this, then the angle between those two tangents will be equal to the angle between those two points. That is a property you have learned in your 10th standard. So again, because of that, angle being equal and the two sides being similar, or two sides being same in both triangles and angle being same, we can use the angle-angle similarity rule and say that these two triangles are actually similar. So because of that particular relation, we can write down that theta will be equal to, in that particular triangle, it is arc length by radius. Arc length is taken as S. When we take a really small triangle, it will be, the curve will be equal to that particular side. So that is why theta is equal to S by R. S is nothing but displacement. Using the same similar principle, we took the opposite side here, that is delta V divided by any one of these two vectors since they are same. So delta V by V, and since it is both theta, since theta is same in both triangles, we can write S by R is equal to delta V divided by V. Dividing throughout by T, we will get the equation for centripetal acceleration. So I certainly hope that you have understood everything about centripetal acceleration, linear acceleration, angular velocity and linear velocity. I hope there is no confusion, and that is all about this particular chapter. We will deal in depth what are the missing quantities, what are the things we have not mentioned in this particular chapter in the coming chapters. So until then, I'll see you. Thank you.